Okay, we can probably do that. Okay. So our next speaker is Professor Sugawa from Tohoku University, who will speak on the space of finite Blaschke products and the Schur algorithm.
Yeah, thank you very much for introduction. So, yeah, first of all, I'd like to thank the organizers to invite me to this wonderful series of workshops, and especially on this workshop on Blaschke products and in the functions. And yeah, just it's pity that I couldn't visit Canada in this time, so due to the COVID-19 pandemic problem. Yeah, in the near future, I'd like to visit there. Okay, so today I'd like to talk about the finite Blaschke products and more generally the so-called Schur class. And in terms of the, I would like to understand those spaces in terms of Schur, so-called Schur algorithm. Yeah, and my talk consists of three sections. The first, we will review the space of Blaschke products of degree D, and second, we will see what is the Schur algorithm, or what are Schur parameters. And in the last section, we somehow will look at the topology of the Schur class in more detail. Actually, maybe I will give my first result in the first section, but the proof will be given in the last section. Okay. So let us see the space of Blaschke products of degree T, and and the function of this form is this well-known analytical automorphism of the unit disk in the complex plane. This is just disk automorphism in the following, and for every point in the unit disk, and the function of this form, just the default products of this kind of disk automorphism and some unimodular constant will be is called Blaschke product of degree D. So this is a standard definition, and here are a couple of preliminary observations about the Blaschke products. So here are some topological characterization of Blaschke products. Yeah, of course, there are several such properties, but we will take one such property here. So this theorem here said that analytic map F of the unit disk into itself is a Blaschke product of degree D if and only if F is proper. That means the pre-images of compact subsets of the unit disk are again compact, and of degree D, or here the degree D means the topological degree, or in a slightly different expression, we can say that this equation for given W has D roots in the unit disk, counted according to the multiplicity. Okay. So this is rather intrinsic characterization of Blaschke product. By using this, for instance, we can see that if F is a Blaschke product of degree D, then so this this function composited with the disk automorphisms L and M from this is again Blaschke product of the same degree D. But of course, this property is valid only for finite Blaschke product. For the infinite Blaschke product, of course, this doesn't hold anymore. Okay. So the space of let's see the space of the Blaschke product of degree D and also degree at most D. So we will denote by this B sub D, the set of Blaschke products of degree D. And also we consider B D tilde, which is the union of these spaces up to D. Okay, and these spaces will be equipped with the topology of locally uniform convergence of the unit disk. And probably it is well known that this space is a compact Hausdorff topological space, but I think that the topological structure of the space is not well studied. And at some time, I was interested in the topology, and then I came to the present study. Okay, and for instance, but to understand the topology, we have some sort of difficulty sometimes. For instance, we consider this automorphism given by this form for fixed data. And so let's think about what happens when A goes to some boundary point of the unit disk. Okay, so let's say e to the power I theta, it. Then the function, this function tends to a constant function, locally uniformly on the unit disk. Therefore, in some sense, the degree of the mapping somehow breaks down to 0. So we have some sort of degeneracy phenomena when some parameters goes to the boundary. So this makes the topology a bit complicated, I think. So how to understand the topology? But on the other hand, we can make the following observations. For instance, for instance, maybe the simplest one is just B node, and this is just a set of unimodular constants, which is obviously the same as the unit circle. This is very simple. And what about B1? B1 is just the set of disk automorphism. And each member of this class has the following expression. Therefore, each function may be parameterized by this unimodular constant and also some point A in the unit disk. So roughly speaking, this space is same as this product. I mean, unit circle times the unit disk. Therefore, this is a topologically solid torus. Solid torus. Something like this. And so what about the union here? Union of this one and this one. So in some sense, the solid torus may be topologically the same as the S3 minus some circle S1. In some sense, yeah. Yeah, I think this is fairly easy to see this topological equivalence. Therefore, if we add B naught here, then we expect that this B1 tilde is homeomorphic to the 3 sphere. So we expect this very simple topological observation. Okay, so actually, this is true for every degree D. So this is our main theorem. So this union is homeomorphic to the D2 plus 1 dimensional sphere, like this. This is a first main theorem in this talk. I'm honestly speaking, I'm not an expert in this field. Therefore, I suspect that this was already known. Yeah. So if somebody knows about this, so maybe I'll be happy to know about it. So please tell me later if you know. Okay. So here is a small remark about known result as far as I know. So in the book entitled Finite Blaschke Product and Their Connections, written by Professor Garcia, Mashweki, and Ross, described the related space, say BD naught of Blaschke products F of degree D with this normalization. So somehow this normalization killed the rotating factor, or maybe the and the symmetric quotient of the set of D tuples of zeros of F, or the set of D tuples of the critical points of Z times F. So these sets may be used as a parameters of the Blaschke products of degree D with this normalization. So therefore, the topologically, it is same as the default symmetric product of the unit disk D, and which is known to be homeomorphic to this polydisk. Therefore, we observe that this space is topologically same as this one, and then by using their result, maybe the result, we know about this. Yeah. At least, yeah. Yesterday, in the Oliver's talk, he mentioned some result of Heinz and some others in 1960s. So I think that this is a rather old result, I think. Yeah, therefore I suspect that this theorem is already known, I think. But anyway. So let me proceed to the next section on Schur algorithm. Okay, so let me introduce some basic notations or symbols. Firstly, the closed unit ball of the Hardy class H infinity will be denoted by S, and which is called the Schur class. So the point is that we allow the equality here. That means this this class contains the unimodular constant as well. And of course, this set may have several different topologies, but here we consider only the topology of local uniform convergence on the unit disk, so that this space is compact. And so how to understand this space in a standard way, in some sense. And one possibility is to think about the Taylor coefficients, Maclaurin coefficients of the functions of this class. So each member F of this class may be expanded in this form as a power series. And we can take the set of coefficients. So this is a sequence. But it is not so obvious, which sequence appears as coefficients of function in this class. Yeah, of course, we have some necessary condition like this, but this is not enough to characterize the coefficients of those functions in S. For instance, we have, for instance, this sort of inequality, which comes from the Schwartz lemma, for instance. Therefore, a Schwartz-Pick lemma, let's say. But anyway, this sequence is not necessarily convenient to parameterize or to understand the topology of the Schur class. And in this, I mean, regarding this class, perhaps it is more natural to take the so-called Schur algorithm or Schur parameters. Okay, so for function f, which in this class, but not the unimodular constant. So we exclude this for a moment, and then we consider this function. So first we take this sort of in some sense, this part is f post-composed with suitable disk automorphism, so that the 0 goes to 0. Therefore, we can divide it by z here to get a bounded analytic function on the unit disk. Yeah, of course, in this form, z should be non-zero, but if z is 0, then maybe we can take a limit. Then we have this definition. And so as we observed, this function sigma f belongs to the Schur class again. Okay, and for unimodular constant, maybe for convenience, we set sigma f is just 0 as a convention. Of course, maybe there is no reason to put to be 0, but this is just a convention. Okay. So in this way, anyway, we define a mapping of the Schur class into itself. Okay. And it is not difficult to see that this sigma maps the set of Blaschke product of degree d onto that of degree d minus 1, and also the the pre-image of this class, I mean, of degree t minus 1, is exactly the Blaschke product of degree d. So in some sense, this maps in some sense, well behaved for the Blaschke products. Okay. And so since sigma is a self-mapping of the Schur class, therefore we can iterate this operation, and we define inductively f sub n by letting this, and we start with f. Okay. In this way, we have a sequence of functions in the Schur class, and we put gamma n to be the value of the function f sub n at the origin. Okay. And so now we can consider the set of these numbers, and we consider the sequence of these numbers, and these are usually called Schur parameters. But in this talk, let us call it the sequence, the Schur vector of the function f. Okay. Here we will use this notation. Okay, so n naught means the non-negative, the set of non-negative integers. Okay. Therefore, we have a sequence of the points in the closed unit disk, like here. Okay. So the maybe it is maybe it is a basic fact that the Schur vector of this function f1, I mean sigma of f, is nothing but gamma 1, gamma 2, and so on. So this is the backward shift of the original sequence here. So this is maybe this fact will be used afterwards implicitly. Okay. And here is a basic result about Schur parameters. So for a function f in this class, the Schur vector or Schur parameters satisfy one of the following two conditions. So in some sense, we have the dichotomy. So the first possibility is that all parameters have modulus less than 1. Okay, this is first possibility. And otherwise, so there are some d for which the gamma d has modulus 1. And but in this case, the other one, I mean the former one has the modulus less than 1, and later one, all 0. Okay. But this is just due to our convention. But anyway, we have this possibility. And moreover, so this, I mean, this happens precisely when f is a Blaschke product of degree d. So this is a very important point. And conversely, if you are given a sequence which satisfies one of these two conditions, then there exists a unique function f in the Schur class such that its Schur vector is the same as this given one. Okay. This is a basic result due to Schur. And in what follows, we will denote by x naught the set of all vectors satisfying one of the above two conditions. Okay. Or in other words, this set is the Schur vectors arising as the Schur vectors of functions f in the Schur class. Okay. The point is that x naught is not necessarily the whole space. I mean, whole space is just this is a subset of this, but not equal. And also, this space is not not necessarily homeomorphic to the Schur class. I mean, if X naught is equipped with the relative topology of this set. So this is some sort of difficulty. Okay, so maybe this part is just a proof of this Schur's theorem. So maybe this is not so relevant with the later topics. Therefore, maybe I will skip it. If I have enough time, then maybe I may come back to this place. But this is a bit complicated. So and also it's standard. Therefore, maybe I will omit it. Okay. So let me move to the last section. Okay. So now let us consider the topology of the Schur class. How to understand it? The Schur class S is equipped with the topology of local uniform convergence on the unit disk D, as I said. Therefore, this S is a compact separable metroidal space. And we would like to understand this topology in terms of the Schur parameters. Okay. And firstly, we observe that this space, I mean the set of Blaschke product of the degree D, may be identified with the set of the Schur parameters of this form. Here, the first D parameters have modulus less than 1, and the last one has modulus 1. And this set may be expressed as this form. This was actually implied by the Schur's theorem. Okay. And therefore, the Schur's theorem implies that this X naught is just a union of this kind of set, and also just a direct product of the interior of the unit circle. However, the topology of this is not necessarily the same as this one, as I said. But at least at this stage, we see that this set of Blaschke product of degree D is homeomorphic to this one by using the Schur's theorem. So this is okay. But we would like to know about the BD tilde, I mean the set of Blaschke products of degree at most D. Okay, so let us first introduce some sort of equivalence relation as follows. So let us consider two vectors, gamma and delta, contained in this set. And they are said to be equivalent and written by this symbol if either these two are exactly the same, or there is some n such that these vectors are the same up to n minus 1. Okay, up to n minus actually up to n, but up to n minus 1, they are in the unit disk D, and for n, they are same and also lie on the unit circle. So we don't care about the later values, for instance, gamma n plus 1 and so on. We don't care. So this is obviously the equivalence relation on this set, okay? And then the capital X will be the set of all the equivalence classes, let's say this one. And let pi be the canonical projection, or canonical mapping. I mean, the pi of gamma is just the equivalence class to which gamma belongs. Okay. And also capital X will be equipped with the quotient topology. So that canonical projection is a continuous open mapping. And by the definition of this equivalence class, this restriction of this canonical projection to X naught is actually bijective. But still, okay, anyway, this capital X is homeomorphic to the Schur class, but still it's not so easy to understand the topology. So actually I think that my contribution is to introduce the following, in some sense, the coordinates for the Schur class and the set of Blaschke products. Okay. So for the later convenience, we define gamma star by this formula. Okay. For gamma in the closed unit disk. So gamma star is just this quantity. So this looks a bit weird, but this is actually very useful. And for given vector in this set, we define a sequence x0, x1, and blah, blah, by letting this one. So more precisely, the xn is defined by this one. Okay. Just gamma n times these quantity. So this is nothing but the gamma one. Bit bit artificial, but anyway, we consider this quantity. And now we can state our main result. Maybe let me remind you of the definition of this mapping. This mapping is very important. So this vector will be denoted by capital E of gamma. Okay, capital E of gamma. So the main theorem says about this mapping capital E. Okay, and we denote by capital Y the closed unit ball of the space, small L2, little L2 on N node. Okay, so this is just a sequence, complex sequence with the finite L2 norm. Okay. Oh, maybe I didn't write it, but L2 norm is, of course, as you know, this is just this one. Okay, and in what follows, Y, this space Y, I mean the unit closed unit ball, will be equipped with weak topology. Okay, not the norm topology. And with weak topology, this set becomes a compact Hausdorff space by using the Banach-Arrow theorem. And our main result can be stated as follows. So this capital E maps this set to Y continuously, and restriction of this mapping to X node is bijective. So X node is in some sense the same as the Schur class as a set. And moreover, this mapping maps this set. This set this set corresponds to the BD. Okay. So this map E maps this set to this set. It's a bit complicated, but essentially, this is this condition said that this is contained in S. This space SD, the D2D plus 1 dimensional sphere in some sense. But additionally, we have this condition. Okay. And in particular, by using this sort of result, we see that this maps this set homeomorphically to this one. So because this maps this set to this one. So and last coordinate doesn't vanish. Therefore, if last coordinate vanishes, then the point may correspond to the Blaschke product of lower order. Okay, and by using this fact, finally we get this conclusion. This is our main theorem. And by using this, we have we may prove the theorem here. This was stated in the first section. Okay. So maybe I have around 5 minutes, so let me tell you how to prove the main theorem. And some part might be interesting in itself. Okay, so here is a small lemma, but this is in some sense crucial result. So if we consider xj are defined in the definition of this mapping capital E. Okay, please recall this one. And if we consider this summation, and then this may be expressed by this form. This is rather different, but anyway, this can be shown by using just a standard induction argument. In particular, letting n tend to infinity, we get this relation. Okay. Therefore, in particular, we see that if gamma n, all gamma n contained in the closed unit disks, then this sum is at most 1. Therefore, this vector is contained in the closed unit disk of L2. Yeah, where? This is one result, and here's another one. So this is also a simple proposition. So it said that for two vectors, let's say gamma and delta, so the images are the same if and only if these are equivalent. That means the both in some sense, the both correspond to the same Schur function. Okay, this is also the simple. So maybe just I will skip the proof. And this slide said that this is also a bit technical lemma. But maybe this lemma is in some sense important. So if the sequence satisfies this condition, and then there is a vector of this form such that this is satisfied. And also again, this is shown by just straightforward calculation. For instance, by using the previous lemma, we have this relation, and by using the maybe this is n minus 1. Oh, sorry. Maybe this is maybe I was just confused. Okay, maybe due to the time limitation, I will also skip here. But by using the induction argument, we can show this result. And so this slide corresponds to the maybe second assertion of the main theorem. And if we have the point here with this condition, then as we saw before, we can construct the sequence xj, and then if this is contained in the sphere, then actually we have this relation. This means gamma d star is 0. That means gamma d is in the unit circle. So this is, in some sense, the key point of the result. And by using this lemma, we have this part of this is a part of the main theorem. Okay, so maybe just let me finish my talk by say something about surjectivities. As for the other part, it's more or less easier. And maybe last slide is a bit more concrete computation, but maybe just I'd like to finish my talk by showing this slide to you. And thank you very much for your attention. That's all.
Thank you very much. Questions, comments? If you have a question, then please just go ahead.
I have one question about Schur sequence.
Mm-hmm.
The theorem that you mentioned by Schur says that there is a correspondence. If you have a sequence, it gives you a function, the unit pole. Is there a result that says by looking at the sequence, you can say it's an inner function?
Uh-huh.
I haven't seen anything like that. I was wondering if you know about this.
Yeah, that's a very interesting question, but unfortunately,
Yeah, here it is.
don't have any answer. Yeah.
No, I haven't seen anything like this. I was wondering if you are aware of any such result.
I have never thought about it. Yeah, but certainly it might be interesting. But maybe it is very difficult question, I think, to answer.
I imagine, yeah. Thank you.
Hi.
Hi.
Can you hear me?
Yes.
Yeah. Oh, okay. I think Curtis McMillan, when he did something on dynamics on the unit disk, he actually also looked. He was looking at the parameter space of finite Blaschke product. Do you know about this work?
Actually, I do not know. Yeah.
Oh, okay. And so I will try to find the reference and send it to you tomorrow.
Oh, yeah. Thank you very much. Yeah.
Yeah. Okay.
I appreciate it very much.
Yeah.
Thank you.
Other questions? If not, then let's thank our speaker again.
Thank you very much.